Good morning, everyone. So okay, can you hear me? Okay. There's not very many people here today. I'm going to wait a couple more minutes, see if we can get some more people to join. Okay, we have another person. All right, well, your quiz was due last night. Hopefully that went okay for everyone. I will take a look at the grades today. I haven't had a chance to look at them yet. So that will be good. Next week, I'm going to pull up our schedule real quick and kind of look ahead. Okay. Next Monday, you have an exam. So that is something to look forward to. I know, not actually, not next Monday, the Monday after next. Sorry, I did not mean to scare you guys. Next Monday, you have a quiz. No, it's kind of weird because that's over fall break. Let me look at the calendar real quick. Fall break is the 19th and the 20th, I believe. How about this quiz only will be on the 21st. So make a note of that. I'm postponing your quiz 6 until the 21st. That way you're not taking it over fall break. You'll take it after fall break. So just to give you a little bit more time and to actually have a couple days off. So please make note of that. I'll still probably have the quiz up and available for you, but I won't have it due until Wednesday. So that's what we have to look forward to. Let's do our attendance. So when I call you, please just unmute yourself and let me know that you are here so you have credit for being here today, okay? Kayla.
Here.
Thank you. Reagan.
Here.
Thank you. Kelsey. Is Kelsey Amal here? Okay. Tana. I know we are missing some people today. Stevie.
I'm here.
Thank you. Josh.
Here.
Thank you. Joel.
Here.
Taylor Lobeda.
Here.
Thank you, because I thought I saw your name pop up. Taylor Lavelle.
Here.
Okay. Grace. Grace. Okay. Andrew. Okay. Amber. Jimmy. Win.
Here.
Thank you. Marissa.
Here.
Thank you. Jamie. Okay. And Jeanette.
Here.
Thank you. Morgan.
Here.
Thank you. Macy.
Here.
Okay. Let's see. Ayla. Elijah. Oriah. Ava.
Here.
Thank you. Well, we have a little bit of a smaller class this morning. That is okay. Just looking forward, we will have class in person on Thursday. I had a little sinus thing and just thought it was safer, just in case, not to have in-person class yesterday, so I postponed it today, and I'm feeling much better, so there's nothing to worry about. It was the allergies. I have horrible allergies. I'm allergic to everything in Nebraska, so with the storm and the wind, it really just kicked it up for me. So feeling much better, so we'll be meeting in class this Thursday. Okay, so on to lecture. We stopped when we were talking about coagulation. So we were talking about the 3 phases of hemostasis. Oh, did something just pop up? Okay, so the 3 phases. So coagulation is the 3rd phase. So why don't we back up for just a second and review. This is gonna work. The 3 phases. So we have, come on. Okay, so the 3 phases. Vascular phase, platelet plug phase, and then coagulation phase. So we've gone over the first 2. We're going to go over coagulation today, and I did a lot of searching to try to find some videos on YouTube that would be helpful. I found one of a professor who drew out his lectures, and they're actually kind of helpful to see it. So we're going to watch one of those today, and that's what we have to look forward to. So I'm just going to skip through vascular and platelet phase because we've already kind of covered that. Okay, coagulation phase. And let's get a little bit of coffee first. Yay for coffee, right? Okay. So the coagulation phase is the third phase of hemostasis, and this happens about 30 seconds or more after an injury occurs. And these depend on clotting factors. So clotting factors, we're going to talk about those today. And I don't want you to get overwhelmed because there are a lot of clotting factors, but just appreciate that there are so many factors that are involved in this process of blood clotting. Okay, so different clotting factors: calcium ions and 11 different proteins are all involved in the blood clotting coagulation phase. Proenzymes are inactive enzymes or zymogen. Oh, somebody came in. So if you are joining late, please remind me at the end of class to update your attendance so you get credit for being here today. I don't want you to miss out on that. Okay, so backing up, clotting factors: calcium and 11 different proteins. So we're going to talk about the importance of calcium and these different proteins today. Then it also depends on proenzymes, which are inactive enzymes, or another name for them are zymogen. We're just going to stick with proenzymes. Proenzymes are converted to active enzymes that then direct this clotting response. So there's a lot of different steps that occur in the clotting or coagulation phase. Okay. There are three main pathways to the coagulation phase. You have the extrinsic pathway, and we'll talk about each of these in just a little bit. The intrinsic pathway. Excuse me. And the common pathway. I don't know what it is about when I Zoom with you guys, I yawn. I am so sorry. I should have more coffee before our classes. Okay. There's also the coagulation cascade, which we will cover. And so these are the videos. We'll come back to these videos. Your lecture has been updated, so these video links are there. And I also included, I'm just going to go back to our class page real quick. I updated in the modules, there's some extra video links for blood clotting. So there's blood typing video, hemolytic disease of the newborn, blood clotting video, hemostasis, intrinsic versus extrinsic pathways. And then down here is the crash course in blood type 1 and part 1 and part 2. So you have a lot of video links that are helpful for you as you're studying. We're not going to be watching all of these, but they're here for resources. Okay. So we'll come back to the video and watch about the coagulation cascade. But actually, this video here, the one below, is short and it talks more about the platelet phase. So we'll do that one real quick and then continue on with coagulation. And then we're done talking about coagulation, we'll come back and watch the coagulation cascade video, which should hopefully help kind of illustrate some of the things we've talked about even more. So bear with me for a second.
Yep.
Okay, are you able to see the YouTube screen? Someone please let me know.
No.
Okay, let me fix that. Thank you for letting me know. Okay, you should be able to see it now.
Yes.
Thank you. Okay. So this is short and sweet. Here we go.
Different than the kind of acts of imagination that go with fiction, because history actually happened.
Do you remember tripping over as a kid and cutting your knee, and then magically the bleeding suddenly stops? Or have you ever wondered why this happens? Our body is very clever, produces substances to seal off the open wound. In this video, we are going to look at how and why blood clots. Clotting prevents us from bleeding to death, and also protects us from nasty disease-causing organisms called pathogens entering our body. When we injure ourselves, we can damage the blood vessels just below our skin. This can cause blood to either leak into our tissue and form a bruise, or if the skin is broken, to openly bleed. To prevent these horrible things happening, blood clotting occurs. So let's have a look at how this happens. Starting with platelets. These are tiny cell fragments that float around in our blood. When a blood vessel is damaged, collagen is exposed. This collagen exposure attracts platelets to the injured area. The platelets then stick together to form a plug. They've quickly built a barrier that stops us from losing too much blood. However, this platelet plug isn't that strong, so it needs to be made stronger. A protein called fibrin does exactly that. In our blood, there are soluble fibrinogen proteins. At a wound, these soluble fibrinogen proteins are exposed to outside chemicals that aren't normally found in blood vessels. Like with the collagen and platelets, this exposure causes the fibrinogen proteins to turn into sticky fibrin fibers. The fibrin fibers form a mesh, holding all the platelets together and making a much stronger clot. More platelets, red blood cells, and other components in our blood all get stuck to the mesh, making it even stronger. This clot stops more blood escaping the body and also prevents nasty pathogens entering our body from the outside. The clot develops into a scab, which protects the wound as it heals, and new layers of skin form underneath. So really, all a scab is just platelets trapped in the fibrin mesh. It is like putting a plug in a sink. When the new skin is fully formed, the scab will fall off, revealing the lovely brand new skin underneath. A final thing to note, remember that I said the exposure to the collagen causes the platelets to stick together, and the exposure to the outside chemicals causes the fibrinogen to turn into sticky fibrin. Both the platelets and the fibrin only become sticky after the exposure. This means in a normal, healthy blood vessel, they won't randomly cause clots. So from this video, you should understand the magic of blood clotting. Platelets are first to the scene, closely followed by the fibrin fibers. Our blood clots so that we don't lose a lot of blood, and don't let lots of nasty pathogens into our body if we cut ourselves.
If you like the video, give it a thumbs up.
All right, so it's just short, kind of just illustrating the blood clotting process. It was not very detailed, which is fine because we go over plenty of detail. You should be able to see our lecture screen now. If someone can let me know, I'd appreciate it. Whoops. Okay, I see chat. Yes, thank you, Ava. Okay, so 3 pathways: extrinsic, intrinsic, and common. Here we go. If my computer will work. There we go. So at first glance, this is kind of busy. There is a lot going on. So I want you to look at the big picture first. So we have the intrinsic pathway, extrinsic pathway, and down below basically is our common pathway. So we can divide this up. So we're going to talk about each of these separately, and then we're going to talk about how they're related. So first of all, with the intrinsic pathway, this is when there's actually damage to the blood vessel surface. So like we just saw in the video where the vessel is damaged and collagen fibers are exposed. this will start the intrinsic pathway of clotting factors. Now, I'm sure you're wondering, how much do I need to know? Bear with me as we go through this. Try not to get overwhelmed with this slide, okay? So a couple of things I want to point out is where calcium is. Calcium ions play a really important role in all three pathways. When we talk about each of these pathways separately, we'll talk a little bit more about what calcium does. But this is one of the roles of calcium in your blood. It plays a role in the clotting process. So you guys should play a game. Count how many times I yawn. It might be entertaining. I don't know. Okay. So, oh, another person just came in. So if you're just joining, please remember to stay at the end of class so you get credit for being here today. If you don't, then I'm not going to remember to give you your attendance. Okay. So calcium plays a really important role. So intrinsic occurs when there's actual damage to the blood vessel surface. Extrinsic, so intrinsic, think inside, okay? So blood vessel surface. Extrinsic is when there's tissue damage. So extrinsic, X, think outside. It'll kind of help you remember the differences. Both of these have calcium that play a role. And they activate different clotting factors. But ultimately, if we look down at the common pathway, which is what both the intrinsic and extrinsic pathways have in common, they both have in common the clotting factor 10, or X. These are Roman numerals, okay? So they both have 10 in common, and they both convert 10 to 10A. And then from there, you start the whole process of converting chemicals into fibrin fibers. Okay, so we'll go through these now. Okay, so extrinsic pathway, this is when you have damaged endothelial cells. So endothelial cells, these are the cells that are lining the blood vessels. Okay, endothelial, inside. So damage to the endothelial cells or peripheral tissues. So when there's damage to either one of these, it releases clotting factor 3. Tissue factor 3. Tissue factor 3, with the help of calcium, undergoes a couple changes. It causes clotting factor 7 to convert to 7A. Then with the help of calcium again, converts tissue factor 10 to 10A. That's where then you go to the common pathway. Okay, so with the extrinsic pathway, what do you need to know? You need to know what kind of tissues are damaged, that it releases tissue factor 3. Tissue factor 3 ultimately, with the help of calcium, activates factor X to XA. From XA, then we go to the common pathway. Okay, with the intrinsic pathway, pardon me. Okay, quick coffee. So this is where we have proenzymes. These are inactivated enzymes. So this pathway begins by activating proenzymes when they're exposed to the collagen fibers, okay? So we have proenzymes convert to enzymes. This happens when collagen fibers are exposed, just like we saw in that video. Platelets, when they attach and rupture on these exposed collagen fibers, release platelet factor number 3. Then you have the enzyme complex of the different proteins that ultimately activate tissue factor X to XA. So we're going to go over this a little bit more. But first, what do you need to know on this slide about the intrinsic pathway? This is where proenzymes are activated when they are exposed to collagen fibers. When that happens, platelets, they're going to bind to those exposed collagen fibers, they're going to burst, and they're going to release platelet factor 3. This ultimately leads to the activation of tissue factor X. Okay. Then to the common pathway, this begins, it doesn't matter if it's intrinsic or extrinsic, sorry. This begins with the activation of factor 10. Factor 10, when it's activated right here, becomes 10A, activates the prothrombin activator. And so what this does is that it converts prothrombin to thrombin. Then with the help of calcium, thrombin converts fibrinogen to fibrin. So that's where we get our fibrin. Notice again that calcium plays an important role in these conversions. With the fibrin fibers, they help form that blood clot that we watched in the video. That helps stabilize the platelet plug, put the fibrin fibers there, helps hold it together and form a scab. Okay, so looking at a different visual, this is showing you the difference between extrinsic and intrinsic pathway and the common pathway. So I like this one because it just kind of illustrates it a little bit differently, and it shows you again where calcium plays an important role and which factors are important. And this might be a picture that I use for your quiz or your exam. So I would study this one. This is in your notes. This is in your PowerPoint. And I would know each step in this picture. Okay. How to best study for this is probably repetition. You could do flashcards. I would really consider a study buddy. I know you can do that online. You can FaceTime, you can Skype, you can Zoom with each other and quiz each other on these different steps. Okay, so just going over the pathways again, starting with the extrinsic pathway, starts with tissue damage. That causes the activation of factor 3. With the addition of calcium, you activate factor 7, which then activates the tissue factor complex, which activates factor 10. So this is a little more simple than the previous slide. If we go over to the intrinsic pathway, this is going to be triggered by the platelets and the contraction of smooth muscle cells. You have tissue damage again. Proenzymes, remember proenzymes are the inactivated enzymes. When they become activated due to the collagen fibers, collagen. They're activated when exposed to collagen fibers. Platelets, when they're come in contact with those exposed collagen fibers, release platelet factor 3. Then with calcium, factors 8 and 9 are activated, which then activate factor 10. So both of these, the extrinsic and intrinsic pathway, take you to a common final point, which is your common pathway. Both pathways take you to the activation of factor 10. From factor 10, it's a very quick cascade of reactions from prothrombin activator converts prothrombin to thrombin, and thrombin converts fibrinogen to fibrin, which then helps stabilize that clot. So again, this is a very good slide for you to study from. Okay. Thrombin is generated in the common pathway, like we just talked about. And thrombin stimulates the formation of a tissue factor. Also stimulates the release of platelet factor 3 by the platelets. So some of this is a little bit familiar because we just talked about it. So with thrombin, it forms a positive feedback loop that accelerates the clotting process. So the more thrombin that's activated, the more tissue factor and more platelet factor 3 is activated, which causes even more clotting to occur. So clotting has a positive feedback loop. Okay. So feedback control of blood clotting, you have anticoagulants. These are enzymes that actually inhibit clotting. So when there is no damage, you don't want clotting to occur because then that can lead to problems. So anticoagulants inhibit blood clotting. So some examples, heparin inhibits activation of factor 2 of prothrombin. So if you inhibit prothrombin, you cannot convert thrombin. Coumadin prevents the activation of vitamin K. We haven't talked about the role of vitamin K, but just know that this is what Coumadin does. Aspirin inhibits the formation of thromboxane A2. Aspirin is often prescribed to people who have had strokes or heart attacks as a blood thinner to inhibit the formation of clots. Sodium citrate and EDTA prevent calcium ions from doing their job. And we've illustrated in all three pathways that calcium has an important role. Okay, so a little bit more about calcium and vitamin K. These are essential in the clotting process. As we showed before, all three pathways require calcium ions. So if you if you don't have calcium ions present, the clotting process cannot occur. Vitamin K, in addition, is required for the making of 4 different clotting factors. Clotting factors 2, 7, 9, and 10. So if you don't have enough vitamin K, you cannot create the clotting factors that are necessary in this clotting cascade. Does anybody know where you get vitamin K? We haven't talked about the process of it yet, because that's going to be in the digestive system. I was just curious if anybody knew. Okay, well, vitamin K is actually synthesized in your intestines, your large intestines, by the bacteria, the healthy bacteria that live there. So that's actually where vitamin K is synthesized. So having that healthy gut flora is really important, and it's pretty much the only way you can get vitamin K unless you take supplements. Okay, fibrinolysis. This is the process of dissolving a clot after clotting has occurred and healing has occurred. So this relies on thrombin and tissue plasminogen activator. So with plasminogen is activated, it produces plasmin. Plasmin right here breaks down the fibrin strands and breaks down the clot. So let me see here. So fibrinolysis is a quick and easy process compared to the clotting process, and it does not take as much steps. Okay, quick summary of two major abnormal clot formations. A thrombus is when a clot is lodged in a vein, like a deep vein thrombosis. And the clot can block the flow of blood to the area past that clot. When part of the clot breaks free, that's called an embolus. And it will travel through a vein and can get lodged in a smaller vein, which can be really dangerous and cause things like strokes and heart attacks. So these are the two major type of clot disorders that can occur. So I would know the difference between a thrombus and an embolus. Okay, before we talk about the life cycle of the red blood cell, whoops, give me 1 second, we lost our screen. I wanted to go back so we can watch that educational video on the clotting cascade. It's of another professor lecturing, but his illustrations, I think, are really helpful. So give me 1 second while we get there. Okay, I need to share my screen. 1 second. Okay. You should be able to see the screen now. Someone please let me know. Thank you, Reagan. Okay, here we go.
Let's say this is a blood vessel and it's made up of these endothelial cells. Blood.
There's no sound.
Containing the blood. The first thing that's going to happen is that little platelets, which
Let me
are
back up, sorry.
Let's say this is a blood vessel and it's made up of these endothelial cells, the same way that all blood vessels are. And let's say that this blood vessel gets into a fight and it gets a little bit hurt. So the walls break open and the cells now no longer seal the vessel from what's around it. When this happens, we wouldn't want all the blood in this vessel to come pouring out of the vessel because we'd lose way too much blood. And so the body has a method of containing the blood. The first thing that's going to happen is that little platelets, which are circulating in the body, are going to come and deposit there and form an initial plug. So these little things are platelets. But it turns out that this plug is not quite solid enough, and so the body needs a second mechanism to solidify the plug. And that mechanism is what we're going to talk about most in this video. And I'm drawing that mechanism here. What I'm drawing is little fibrin strands, which will come and act as a kind of mesh to hold the platelet plug together solidly. So what do these fibrin strands look like? Well, they're made up of little fibrin subunits. And these are actually what we refer to as the fibrin molecules or proteins. And these, it turns out, have a natural affinity for each other, so that when you bring them together, they form a polymer. They join end to end, and they create a fibrin strand. So the question then becomes, how do you make sure that these fibrin units only join together and make a strand at the site of injury? So for example, if you had a bunch of little fibrin molecules over here, how would you keep them from joining together? And the answer is that you can't, which is why you don't have fibrin circulating in your blood. You actually have something else, which I'm going to draw here. And that something else is fibrin, but plus an extra piece. And that extra piece, as you can see, covers one of the active sites of the fibrin and therefore prevents it from joining to itself. So the name of this thing is fibrinogen, probably because it will form fibrin, hence the fibrinogen. And it's only when you convert fibrinogen to actual fibrin that the units can join together and form a strand. And so again, to repeat, you don't have fibrin circulating in your blood. You actually have fibrinogen. So the question then becomes, how does your body know to convert fibrinogen into fibrin at the site of injury? And the answer is that when you injure your endothelium here, you're going to expose your blood to new proteins. And maybe your actual endothelial cells will release some proteins because they're damaged. So basically, you have new proteins that weren't seen before and that are seen now. And those proteins will eventually cause fibrinogen to turn into fibrin. So while evolution was designing us, it could have said, let's use these little yellow guys to convert fibrinogen to fibrin. That might have worked, but it's actually not the most efficient way to do things. The reason is, imagine if you and a couple of friends have a huge amount of work to do. Let's say you need to convert 1 million fibrinogen to fibrin. Is the best way to do it to actually sit down and crank it out? Or would it be more efficient to have each of you call 5 friends and invite those friends to come work and ask those friends each to call 5 friends and ask those friends to each call 5 friends? Well, obviously that would get the job done much faster, assuming you had those friends. And that's also what your body does. So actually, it doesn't use these yellow guys to convert fibrinogen to fibrin. There's another player which does that, and it's an important one, so we'll give it a little drawing like that. And it is called thrombin. And thrombin, just like fibrinogen, is activated from an inactive form, which we call prothrombin. And the prothrombin has a little piece on the end that prevents it from working. So this is prothrombin. And that piece is removed when you want to get to work. So is prothrombin activated by the little yellow guys? Well, actually, he's not either, because the chain of amplification is much longer than that. To draw out the actual amplification cascade, you just need to see it and practice. But there is an easier way to draw it than it usually is drawn, and so we'll do that now. So let's say you were counting down from 12. Normally you would start at 12, you'd go to 11, you'd go to 10, and then you'd go to 9. But let's say that you weren't very good at counting. You would start with 12, you'd go to 11, you'd make a little mistake, you'd go to 9, then you'd realize you forgot 10, and so you'd go to 10. Now it's good that you remember 10 because 10 is a big deal, and he's going to help bring us thrombin. It turns out that thrombin is also known as 2. And we know very well that thrombin
helps give us fibrin, which is known as 1. And that's no surprise because fibrin's the most important guy. He's the ultimate goal. And thrombin is the guy that helps us get the ultimate goal, so he should be number 2. Now, unfortunately, it's not quite that easy. 10 likes 5 because they're both multiples of 5, so they work together. And 9 likes 8 because they're right next to each other, and so they work together. So this is the first part of our clotting cascade. And it turns out that we call this part here the intrinsic pathway. And we can talk about what that means later, but for now, let's just give it its name. But what's perhaps more important to be clear about is that in this drawing, 12 is not actually becoming 11, and 11 is not actually becoming 9. What's happening is that 12, when it's activated, is a catalyst to convert 11 from its inactive form into its activated form, which we'll draw 11a. And then once 11 is activated, it serves as the catalyst to convert 9 from its inactivated form into its activated form. And so you see that these arrows are actually more about catalyzing. Now, I said that this was an amplification sequence, and so I just wanted to share a little data to show that that's true. So it turns out that this guy, factor 1, or fibrin, in its inactivated form, which is fibrinogen, has about 3,000 micrograms per milliliter in blood, while this guy has about 100 micrograms per milliliter in blood. Meanwhile, 10 has about 10 micrograms per milliliter in blood, and factor 9 has about 5 micrograms per milliliter in blood. And so you can really see that as you go down this thing, you're increasing your amounts in your blood, which reflects the fact that you're also going to increase the number of active forms of these when you have a clot. But anyway, I said that this was the intrinsic pathway because there is another pathway which also leads to an activated 10, but in this other pathway, what activates the 10 is an activated 7, which is activated by 3, also known as tissue factor. I'll just write TF for tissue factor. And this pathway, which I'll circle here, and I apologize for the poor organization, this one is known as the extrinsic pathway. Extrinsic. So what's the difference between these two pathways? Well, it turns out that the extrinsic pathway is the spark. It's the one that gets activated by the original insult over here, whereas the intrinsic pathway is kind of like the workhorse that really gets most of the coagulation done. So how does that work? Well, you first get this tissue factor, which is actually one of these little yellow guys. And that tissue factor activates 7, which activates a little 10. So you get a shot, a spark that shoots down this way and activates a little bit of 10. And then 10 will activate a little bit of thrombin. And then thrombin will get the intrinsic workhorse going. And how will thrombin do that? Well, thrombin actually activates a whole bunch of these guys. And to remember the ones that it activates, you just need to take the 5 odd numbers starting at 5. So what is that? That's 5, 7, 9, 11, and 13. Actually, this is just almost right, but it actually turns out that it's not 9, it's 8. Because it couldn't be quite that easy. So those are the 5 that it activates. And so let's draw that in here in our drawing. So let's draw that in the form of blue arrows because thrombin is blue. We said it's going to activate 5. We said it's going to activate 7. We said it's going to activate not 9, but 8. So this will be an awkward arrow to draw. We said it's going to activate 11. And we said it's going to activate 13. Where's our 13? Well, we haven't actually drawn it in yet. So let's quickly chat about that. The end goal of this whole cascade is to get these fibrin molecules. And these fibrin molecules together will form some strands. But it actually turns out that there's one more step, which is to connect these strands together. And so we're going to want to connect these strands together with some crosslinks. These crosslinks will just hold them together so that they actually form a tight mesh. And it turns out that it's this step right here, which is enabled by factor 13. And so let's draw the final thrombin activity, which is to activate 13. So you can see that once you activate a little thrombin, it's going to activate all the necessary things in this intrinsic pathway to get it going. And you might actually be wondering about 12 up there because thrombin is not hitting him. And actually it turns out that if you remove a person's factor 12, they can still clot pretty well. And so it's clear that 12 is not a totally necessary part of this intrinsic pathway. And to be clear again with our use of arrows, this green arrow here is different from these white arrows in the sense that here we are saying that fibrin is going to become fibrin strands, which is going to become interlaced fibrin strands. So if this was all there was to the story, then every time you had a little bit of damage to your endothelium, you would cause the extrinsic pathway to fire. And so you would create a little activated 7, you would activate some 10, which would activate some 2, which is thrombin, which would start to create fibrin from fibrinogen. And moreover, the thrombin would have this positive feedback, which would cause more and more thrombin to be produced, which would cause more and more fibrin to be produced. And basically, this system would just spiral out of control and you would become one large walking clot. So to keep that from happening, there are some negative feedback loops. And like much of the other steps in this picture, they're governed by thrombin. So one thing that happens is that thrombin helps create plasmin from plasminogen, much the way it helps create fibrin from fibrinogen. And this plasmin acts directly on these mesh networks of fibrin and breaks them apart. So that's one helpful factor, but that's not really an example of negative feedback because it won't prevent the continued production of all this. And so another example is that thrombin actually stimulates the production of antithrombin, which is kind of counterintuitive, but that's sort of classic negative feedback. And what antithrombin is going to do, as you could guess, is it's going to decrease the amount of thrombin that's being produced from prothrombin. And it's also going to impede the production of activated 10 from 10. So what if this whole system didn't work? I don't mean the negative feedback, but I mean the whole clotting system. Well, if it didn't work, then you wouldn't form a stable plug here, and you would get lots of blood pouring out of your damaged endothelium. And so what we call that is hemophilia. Hemo refers to blood, and philia means love. So people who have hemophilia love to bleed. And there are 3 different kinds of hemophilia. There is A, there's B, and there's C. And it's easy to remember the causes of these because A is associated with 8. B is associated with what comes after 8, 9. And C is associated with what comes after 9, not 10 actually, but 11. And so we can draw those into our clotting cascade over here to see that a factor 8 deficiency will give you hemophilia A. A factor 9 deficiency will give you hemophilia B, whereas a factor 11 deficiency will give you hemophilia C. And so we see that these guys target the intrinsic pathway.
Okay, so I know that was busy, but I think he described it really well.
My name is Scott
Oh, stop.
Harris.
Okay, sorry, I'm having trouble.
This is my
There we go. I really liked how he illustrated everything. I would use that as a study tool. Pretty much everything he talked about is what you will need to know. Okay. All right, sorry, we're on the wrong slide. Okay, so really quickly, we're going to kind of go over the life cycle of the red blood cell and how it's broken down. So the average lifespan of a red blood cell is about 120 days. And So a couple of things can happen in the bloodstream. If red blood cells rupture, that's called hemolysis. We've talked about that already. You have old and damaged red blood cells. About 10% happens this way and are engulfed by macrophages. So this big purple thing is the macrophage. And if you remember, the red blood cell graveyard is in the spleen. Okay. Most of the red blood cells are engulfed by macrophages, and then they're broken down to their individual components. So hemoglobin is a protein, so it's broken down into amino acids. The heme complex is broken down into iron. Iron is transported in the bloodstream by a protein called transferrin. So ferrin refers to iron, and then so transferring the iron. The heme group is broken down into biliverdin and then to bilirubin. Bilirubin travels through the bloodstream bound to albumin. Remember, this is one of those inert proteins in the blood. So bilirubin that's bound to albumin travels in the bloodstream to the liver. Bilirubin is then placed into the bile, gives it that yellow color, and bile is released into the large intestine, well, actually secreted into the small intestine, and then travels to the large intestine and is broken down even further. Okay, so hemoglobin that's not phagocytized in the blood and breaks down is going to be eliminated in the urine. So small amounts are eliminated in the urine, the breakdown products. Bilirubin is broken down in the large intestine to urobilins and stercobilins. Some of that is absorbed into the bloodstream, which is then secreted in the urine. And the rest is eliminated in the feces and actually gives the feces their color. So if you want to watch a short video, I'm not going to do it now, but it's right here in the lecture that just talks about the life cycle of the red blood cell and how it's broken down. I'm not going to ask a lot of detailed questions. I mostly want to know what happens to iron and what's going on with bilirubin and how that is transferred from the liver into the large intestine and then excreted. The important thing to know is that the iron that's transported by transferrin is going to be recycled to make new red blood cells. The amino acids from the hemoglobin are going to be broken down and used for other protein synthesis, including making more new red blood cells. So that, we're going to check our schedule one more time. Okay. Just want to make sure, I think we're ahead, still think we're ahead. So today is, oh, come on, why is this not, there we go. Today is the 13th. Yeah, so we're still ahead. So we are on track. We will slowly get started. We may do a little bit more about blood typing on Thursday, but then we'll probably slowly get into digestion. I know we're ahead, so we'll kind of do some, we'll do some maintenance stuff on Thursday. What I'm gonna have you guys do, since I got that Kahoot thingamajig, is do a quick assignment of asking questions about the blood and blood clotting process, and I'll put that onto Kahoot and we'll do a review, okay? So I'm gonna make an assignment right after I'm done talking with you now. I'm gonna make it do, let's see, when is your quiz? Wednesday. I'm gonna make it due tomorrow night at 8 p.m. so that I can make the Kahoot questions. So I know it doesn't give you a lot of time, but it won't take you very much time to write up a couple questions. So do that, and we'll do Kahoot on Thursday and do some kind of maintenance stuff about class. Are there any questions about today? Questions, comments? Okay, if you arrived late, please do not leave until I've been able to mark you as present. So maybe in the chat section, tell me who came in after 8 o'clock. Oh, looks like a couple of people left already. Haha, they're not going to get credit if they left. Okay, Jamie. So make sure you hear your name, okay? So I got Jamie. I'm trying to wait for the page to load. Okay, Jamie, you are marked present. Who else came in after? Grace. Okay, let me find you, Grace. Great. Grace, you are marked as present. Anybody else? Elijah. Oh, what's your last name, Elijah? I'll figure it out. Let's see. Where are you? Elijah Wagner. Okay, you've been marked as present. Anybody else come in late? Okay, I got a Jamie, I got Elijah, I got Grace. If you are unsure, you want me to check your attendance, you can let me know and I'll check real quick just to make sure that everyone is here and gets credit for being here.
What section did you want the Kahoot questions to be over?
I want it to be over the blood, so the whole blood chapter.
Just blood so far?
Yeah, the whole chapter, which includes blood, blood clotting, a little bit about blood recycling, but yeah, so the whole chapter on blood. So I'll have you guys pick 4 questions. You can pick any topic you want that has to do with blood.
All right, thank you.
Sure. Any other questions? All right, then I'm going to let you guys go. I'm going to create that assignment right now. So you can get going on it now if you want to. So give me about 5 minutes to get it up, and then you can start submitting your questions for Kahoot. And thank you so much for coming today, and I will see you in class on Thursday. Okay, have a good day. Bye.